A very good morning, ladies and gentlemen. Welcome to the first Malaysian International Conference on Nanotechnology and Catalysis 2021. We are now in the plenary sessions. My name is Liu Beifen, a Senior Lecturer and Research Fellow at NanoCat. I'll be the session chair today. Together with me are the session moderator, Dr. Tan Kin Han, Dr. Lina, Mr. Muhammad Nur Iman, and Madam Nurain. Ladies and gentlemen, for those who intend to ask questions to our honorable speaker, you can channel your questions in the chat box. Your question will be raised in question panel and I will read it accordingly. Before we start, I'm honored to give a brief introduction of distinguished Prof. Suresh Bhargava. Distinguished Prof. Suresh is a world-renowned interdisciplinary scientist who has achieved excellence in 5 disciplines and is recognized for delivering research excellence that underpins significant industrial applications. He has published more than 450 journal articles and more than 200 industrial reports. His research has been cited more than 12,000 times, amounting to over 5 citations per day, with a H index of 53. He has been quoted as being among the top 1% scientists in the resource sector and as the #1 in mercury sensing research. Without further ado, I'm honored to invite Prof. Suresh to share on the title, Unlocking Next Generation Catalysis Through Advanced 3D Printing. The stage is yours, Prof.
Okay, so I can probably start from there.
Yeah, Prof, you can share screen.
Share screens is there, right?
Yeah.
How can I start my things? You? Open. Okay, I hope you can see it now. Hello.
We can see you. We can see your screen, Prof.
Okay, that's it. So,
yeah.
Good morning to my Malaysian fellows and probably all of you. I think it is unfortunate that I'm not there in person, which I used to be there for so many years with you. And finally, this conference, which we are planning for such a long time, eventually happened. So I'm very, very happy, very, very pleased to be a part of this conference and a part with you, though virtually in there too. Let me today introduce you a new concept in catalysis, and that is the 3G catalyst. And I will define you what do you mean by the 3G. I will say that is a 3G is a 3-generation catalysis, because catalysis has generated, at the time of Berzelius until to date, it has a long way. It is a part of our human life nowadays. Without catalysis, it is hardly imagined that things can be produced which are needed in our everyday life. So, but what I'm trying to introduce here, 3D additive manufacturing can be introduced, this concept to make this the whole life into the whole life of the catalysis and the industrial manufacturings that they are they can be revolutionized and they can be think about differently, because the next challenge will be with us will be the eco-sustainability of any industries using the catalyst or not using the catalyst. So let us see what is these journeys, what is this new concept, what is this innovation in there, and how we can achieve in the both field. Science and engineering are joining together to make this innovation happen. Okay, because I am not from Malaysia, I am coming from you down under, so I have to introduce you myself, that it is the RMIT University, probably the Australia's largest tertiary institutions. It is located in Melbourne, Victoria, 3 campuses in Melbourne there and 2 campuses in Vietnam, and a strong research collaboration with academia and industries. And I'm sure that you are aware about these names, RMIT Universities. I am the part of it since last 30 years. It is a vibrant university in a vibrant city, but not so much vibrant nowadays because of the COVID-19. There is a lockdown. There is a more or less lockdown or night curfew in Melbourne City. So you can see our campuses, city campuses is quite vacant, quite empty, but I'm very sure that the good days are not far away. You will see that these campuses will be full of the vibrant there too. Now, second things I want to introduce you, that as you introduce me, that is a borderless mind platforms where the pupils are working together for science and engineerings, and even from different discipline of the scientists are working together to find out the solution of a particular problems. In the science area, we find out the missing puzzles, what is missing puzzles, developing the new concept, and then the engineers take it over from there. We have a very good biologist where we can go to from anti-cancerous, the molecular engineerings, where we can design the certain molecules and then see that that those molecules can be working for the anti-cancerous compound. But today, let me focus it that we are basically talk about the 2G, because I know that the time is very limited over there too. So that's it. That is the platforms from where each. That is the platforms what I created about 20 years ago, and that is the platforms which is growing very fast. How fast? Now you can see we usually publish nearly about 121 very highly cited papers. As you can see, our papers goes to the chemical reviews, Nature, Catalysis, Chem with the cover page articles, and this ChemX centers is now connected with about 19 countries with 70 experts all over the world. So we use the power of collective intelligence. We try to develop the intellectual infrastructures to find out the innovations. We always have one emphasis only: find out the solution. The problem is there, whether it's industrial problems and whether it's scientific problems, whether it's engineering problems, when the industries knock our doors, or any of the things like any of the curiosity, questions, fundamentals arise the question on these platforms. We try to take the advantage of our global network to find out the proper answer so that a real solutions can be achieved. Okay. So let me take you these things, this concept, what I was thinking about, that why we call it the 3G. I call it is the first generation of the catalyst at the time of the Bergerius, when the catalyst was just developed, this phenomena, the concept, major discovery was done, many Nobel Prize winners came out. Sir Humphrey says, David Humphrey, when he produced the hydrogens on the metallic surfaces, that this is probably the brilliant discovery, because at the time the light was a major factor there. And then the time comes when this catalyst, this whole concept did the first revolution. The first revolution came when we used the catalytic converters in our car automobiles, because the air pollution was a big issue. And after the catalytic converter use, when the air pollution reduced quite drastically. So that was the major one. And also ZSM5, geolite discoveries, where all the oil industries based upon geolite, ZSM5s. And, there is a couple of Nobel Prize over there too. Well, then the time comes. I mean, those two concepts is done now. I call them as a 2G, second generation catalyst is there. Now the time has comes where the new generations, they are starting that every industry should be eco-sustainable. Where the two phase of any industrial reactions, one phase is the catalyst development, where how far we can go to develop our catalyst, how far we can go, how we functionalize, can be used. Now the nano catalysts are coming up, as you can say that too, how we can use this nano catalyst to the optimum capacity, and also the reactor designs, how we can intensify the process by changing the reactor designs. And if you two combine together, if you two combine science and engineering together, then a real process, a real innovation can happen. I will call them as a 3G catalysis, third generation. And that is exactly I'm talking about. I'm giving you a glimpse because the concept is still very new. Concept is being still developed, but very rapidly is in there too. So I will call them like an industrial 4.0, where the additive manufacturing will comes over there too, is in there too. Okay. So that is our journey. That is the journey, my journey, you can say, or that is the journey of my center over there, which I opened there too. We started from 1994 with there, we are talking about the spectroscopy, geolite, ZSM5, all type of geolites, alpos, sapos, and their FTIR studies, understanding the fractions, understanding the surfaces of these catalysts, trying to develop the high surface area, try to develop the active sites, and try to understand the mechanisms, how the Denox catalyst, how the VOC catalyst can work. And then the catalyst come then we start working on the green chemistry, like the green chemistry, the fine chemicals, which I did in collaboration with my Indian partners quite rapidly. Professor Lakshmi Kentham, she will be the speaker there too. So we start working of different type of the fine chemicals is in there too, using the catalyst again. And then time comes to the working on the air pollution controls, the catalyst in the air pollution controls. And one of the area which picked up, which was not picked up by the many people around the world, because the many people think about is the VOC is a problems. Many things people thinks about it is a NOx is a problem, SOx is a problem, particulate is a problem. Of course there are problems, but there are so many other problems in the air which also causes a lot of problems in the human life, such as the mercury. And that was the mercury from the flue gases. And then we start working on the mercury abatement. And our labs, which is totally dedicated to the mercury sensing, mercury removals there too, is now classified as one of the top lab in the world, is in there too. So it was established, and we have published in the mercury alone area is nearly about more than 70 papers and many review articles. And this technology has been developed, passed on to the industries, licensed to commercializations. So in mercury area, we are very, 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 very strong in there too. Then time comes when we're talking about the CO2 reforming and methane, then CO2 is becoming an issue. People start thinking how we can use the carbon dioxides, and then the CO2 reformings, dry reformings, and tri-reformings, and all those things comes with the methanol economy is coming in the pictures. And then we start using the methanol reformings and oxidation. And here then we start getting a very big projects, about a $6 million with the industries, CSIRO and other partners in Melbourne and as well as in India. Then we're talking about the DME, dimethyl ethers, producing the dimethyl ether using the carbon dioxide, which we using the methanes. And here is the birth of the additive manufacturing started from my end. So we took part there too, how we can do the reactor designings was done. And I'm proud to say this project, which we started about 10 years ago, now it has gone to a stage where one of the industries in India is making the product out of it. Not only they can make the DME, but one of the 3D printed product is now producing the deuterated methanol there as well. Then this additive manufacturing concept in catalysis keep growing at my area. In addition to the additive manufacturing precedents, we have a big programs where the additive manufacturing is going on, and we combine with the catalysis in chemical sciences, and this continues. And the latest discovery, and I will show you that this paper in ChemCom is just published today. It came out just today, luckily, and that is also about the fuel technologies for the high-speed vehicle, flight vehicles. Okay, I will talk about that paper as well, and I will talk about the other papers as well, that how these techniques can go. But the theme of the talk today is there too: 3D catalysis, 3D printings into the 3Z catalysis. And I told you there are two concepts over there. One way we can develop the catalyst, how far we can go the developing a catalyst, how far we can go how we can optimize the catalyst performance. That is a materials development. Second part is reactor developments. What type of designing reactor we can make, which can make the process so intensify, so process can be most efficient and very cost effective. And combining the two will provide you perfect solutions for any industry that they want to make eco-sustainability, which will be the challenge of the 21st centuries, is in there too. Let me talk about it. I mean, that is the book which we are writing, and probably you will see that it will be published from the Nature Publishing Groups, which is the additive manufacturing, a premier of the chemical sciences. It is coming by the end of the year, and I'm sure that I will share these things with you as well. But the idea was there, additive manufacturing is time to the market. If you use the additive manufacturing, which is now becoming quite fashionable, it started about decade ago, about 15 years ago in real forms, and now on it is a part of any of the major or basically advanced laboratories, any centers, they have the additive manufacturing. Very rapidly growing in China, very rapidly growing in Europe, very rapidly growing to US, very rapidly growing to probably everywhere in Australia as well. Most of the universities now. Our additive manufacturing percent is probably one of the oldest in Australia, one of the major one in Australia. It was established nearly about 15 years ago when this concept was started developing as well. So you can see just the alone additive manufacturing, like you can see a lot of papers, a lot of books are coming up. You can see a big plant can be reduced to the tenfold, can be reduced to the tenfold. A small plant. See the space, the efficiencies, the materials, the cost effectiveness, all those things are there. It provides some challenges, and that's why the research for is there too. So now you can see the advantage of all these things, that how we can do the additive manufacturing as a new era in the catalysis. Then I will take to the in catalysis area. I gave you the first picture, the additive manufacturing. But if you can see, we can dope the nanostructure catalyst over there. We can also do the additive manufacturing. We can make the reactors. These all were made at RMIT. They all has been used to have a fuel efficiencies in a manufacturing process over there too. And many of them has been used in the DMA productions. Many of them has been used to the real productions of the, as I told you, the industrial petroleums manufacturing in India. Then other things as well, that all these reactors, for particularly over there, whether it's CO2 reformings, whether you're talking about the hydrogen productions, whether you're talking about the endothermic fuel of the high-speed, supersonic vehicles over there, and all those syngas productions, methanol, dimethyl ether, you start using the additive manufacturing product. Either way, either the catalyst development, either we start doing the catalyst in an additive manufacturing way, that how we can do the improve the catalyst, or in the other way as well, the reactor designing. Sometimes we use both, and most of the time we use both, so that the chemical process intensification can be achieved over there too. So again, I will trying to basically convince you is there that if you look the printed catalytic device, like this is about like additive manufacturing catalysis. So we're talking about catalyst only here, not the process. I'm talking not about the engineering so far. At the moment, how many times, how many ways you can do it. Like if, for example, you can use the fusion of the technologies, like a catalysis, additive manufacturing, and the printing catalyst device, it is going up like 2 times to 2020, 2021. So you can see how rapidly it is going. The other family of the printable catalytic devices are coming up. The catalytic reaction wares, that is coming up. Structures catalyst, they are coming up. You can design any structure of the catalyst, and also advantage of the printable catalytic devices. So you can be inspired by the nature. You can just inspired and then computerized it, and you can print it. Exactly, copy that, and then see the impact. Does it make any impact on your reactions? Does it make the impact on things? Fast productions, the catalytic, most of the times once you are design on your computers, you can produce those devices very quickly without any problem. Smart assemblies, the enhanced mass and heat exchangers, that can be, so several advantages. You can see the advanced geochemistry, whatever the design you can imagine in your mind, and you can translate that imagination on your computers, that can be printed. Whether it is a micro levels, whether it is a macro levels, and whether it is the nano levels. You can design them, you can dream it, you can design it, you can print it, and then you can use it. And then you can see that is my dream is coming to a fulfilled stage. Can I see it? Is over there, how it's going to work. So all those things, imagination, or imaginations about 10 or 15, 20 years ago, and they are becoming reality, is in there too. Let me talk about something like 3D printing techniques is in there too. So that is clearly about the first techniques. This additive manufacturing has also known as the three-dimensional 3D printings work as a additive principles, which means that the solid model of the polymerics, metallics, ceramics, and their possible combinations can be directly made by utilizing a computer-aided device, CAD. We call it a CAD, computer-aided design. Okay, file without the minimum use of the tooling and fixtures over there. This technology has evolved from a rapid prototypes, RP, that was earlier used for the development of the plastic prototypes for design evolutions and testings, concept modelings, and their marketing over there. So you can see conceptualizations, and then over there, design is a CAD designing, export over there, then slice of the models, then you go to the upload of the file of the printers. Here you go, print the objects straight away. And then they can print basically in there too. This acquire a 3D models is in there. Acquire a 3D model file to the STL format and slice the files. The create printer instructions. Build the part is in there too. So you can do all those possibilities now are possible. All those imaginations can become possible. They have been designs by computers, and you can print out is in there too. I will show you that how you can functionalize then those processes as well. But one by one, let us talk about the process cycles first. Then talk about the selectives. As you can see, these videos that you can design in there, the laser beams up to the 100 to the 400 watts plus scanned over the plate covered in the metal powder using the acquainted mirrors under controlled atmosphere, typical argon over there. And one layer thickness is typically about 20 to 90 micrometers. achieve full meltings in build materials allowing 100% density, significant number of the process laser materials, powders and geometry parameters affect the quality of the SLM parts up to the 130 parameters to be of relevance, and focus on the research to develop a comprehensive understanding of the model. You can see is there that whatever we are designing there, once you design that there, you can go to the laser printings and you can print that. Well, you can manufacture there. Here you can also, in these diagrams, you can see as well that how this printed, how this design can be printed. You can use materials, process, laser part. This is the example of the SLM parameter, and that is a selective laser melting that is widely used in making a printed or 3D printed design materials. Either is a reactors or a basically is a catalyst monolith is there. We can dope it there, and I will show you that we use quite often this type of things as well. Okay, then it comes over the printing polymers, fused deposition modelings. FDM is there too, and this FDM is basically process is compatible with the broad range of the thermoplastic materials. These materials exhibit a range of physical and mechanical properties which should be selected in accordance with the desired application requirement. For general engineering application, acronitriles, butadienes, styrenes, polystyrenes, polyacetic acids, and polycarbonates are the preferred materials candidates due to the low cost, good mechanical properties, and compatible with the FDM processing. And recently, FDM materials have been expanded to the biological applications, where the biocompatible polymers such as the polyglycolic acids and polycarbonic carbonic acetones and polybutylienes or terpethylenes, it can be PBT, can be used over there. So here you can show that various examples we can use the printed polymers. We can use that, and that type of printer is not very expensive. In fact, one I have in my own lab as well is in there, where you can use the printed polymers, where these students and the research fellow can play with that. They can design the printed polymers. In fact, some of the printed polymer reactors can be used for certain reactions, because certain polymers are quite unreactives. So they can be used for certain reaction as well. They can printed materials, flow mixtures, photocatalytic reactors, catalytic reaction layers. Sometimes we can also use the vessels for the Raman or the FTIR, FTIR cells as well. We can print those cells as well, micro cells, macro cells as well, using that as well. Then it come out as a printed polymers, photopolymerizations, and that is the technique which is widely used nowadays. And this photopolymerization is an additive manufacturing method in which the liquid photopolymers resins contained in a vat is selectively cured by the light activated polymerizations. You can see is a light activated polymerization. As you can see that light and photoinitiators, the both are going, the polymer reactions opens over there, and you can get the cross-linked polymer solid part over there. So that process keep going over there under the photocatalytic reactions, or you can say it's a photocatalytic reaction, yes, and then you can print it this type of material as well. You can print it all those type of device in polymeric base as well, and then you can also print it all those device into the metallic surface as well. So here you can say for example, the SLA printing key factor is the resins printed. So you can use that. I mean, you can use that as well in this way, and you can make the first phase of those reactor design in polymers. You can use this technique. You can make that. Once you are perfect, you can see it can be used. You can go to any in-column metallic systems, any of the metallic system. Copper, nowadays copper alone can be made, the titania can be made, stainless steel can be made, and also the what I call it, the Inconol is a alloys. Those alloys can be made as well, isn't there too. Now, rope casting, that is probably the most useful method. The additive manufacturing of the ceramic materials, that is now being very, this is a very useful techniques, and this is a very useful materials which is being used by many research areas as well as in the industry as well. So preparing the pseudo-plastic ink ceramic particles, plasticizers and binders, that is the one. You can make all those things by this method. Extrusion through the nozzles on a platforms, as you can see, and nozzle position, amount of the ink per pass, important parameters over there. And you can prepare by sinterings, and in fact you can prepare by the calcination, the high temperature. You can prepare those oil models as well. Now what I'm trying to show you at this times up to now, what I'm trying to show you, by using the additive manufacturings, you can put your imaginations on your computers anything what you can do. And if you can print out your imagination, you can design your imagination on your computer. Yes, you can print it in various forms: ceramics, polymers, metallics, different type of the metal alloys. So all those possibilities are there in front of you. So that will give you the first platforms for the innovations, because here you can see, can I make a plate? Can I make a surface? Can I make a test surface for the catalyst optimizations? Can I make a reactors of any designings where I can take the advantage of the the mass balance? Can I make the heat exchange? All those sort of thing, engineerings, all those possibilities are there, is in there. So let me show you. So choice of the materials, like additive manufacturing, what type of the materials you would like to use. And in this one, then all these materials are chemically inert. Important thing is there. First of all, limited choice of materials, because proprietary polymers, metals, ceramics, they are the only one available. Still the research is going on on various metals. Inadequate of the cater of the chemical process, the complex solutions, that is going on. And therefore, if you want to use those things in the form of in the form of that they want to use your surface for the catalyst, remember that these are the inert materials. You have to functionalize them. And I will show you that how we have functionalized over there too. Therefore, the surface functionalizer is a key strategy to use this material for various applications. If you want to use those surfaces as a catalyst, as a fixed backed catalyst, because this type of catalyst will be far, far better than using a catalyst as a powder, using as a catalyst as a pellet. These type of materials, which allow hardly any iteration of the catalyst, is in there. They will be active, they will be long lasting, they will be cost effective, and you can use them very conveniently, is there too. Like for examples, this is the surface. We did that in this paper as well. Then we can see that we produce that the surface of these materials are not smooth enough. Surface functionalization of these surfaces are challenging. And then what you can do, you can coat that. You can make those surfaces which go as a porous surface, and then you can upload the nanoparticles on there as well. That is possible, and we did that actually. In fact, I tell you one thing as well. When we start using the titanium monolith, is the titanium methylium, that when we start doing the the heat treatment there, we found that titanium is no more titanium, is now titanium oxide. And when it was the alloy of the titanium and the aluminiums is in there, the aluminum concentration on the surface start increasing. In fact, we start seeing also the scene that we start seeing the sign of the titanium aluminate over there too. So those surfaces, before we start heating, before we functionalization there too, on the surfaces after there, they are different and they can be manipulated for your application. That is the article. This is the first article came out when the Catalysis Science and Technology is there in 2017. This is the first article in the literatures when we are claiming 3D printings in the catalysis over there. After that, this area is a boom start. Many times, even the natures and everything, the articles start appearing all the times is in there too. We start doing that, as you say, that was our strategy. Characterize reactions, calcine over there, coated the SLM there too. And in this way, you can see that is the catalyst we use. For example, microtop reactors, and we can functionalize those surfaces. We can use those catalysts. So it's a studies developed to functionalize the surfaces over there, is in there too. And that is the area which we are working for the industries. We can coat many variety of the nanoparticles, sometimes strongly, sometimes weakly. This research is still ongoing process, is in there too. As I told you, the alumina coated the titanium monolith, zinc oxide coated titanium monolith. All these materials are, zinc oxide is a very good catalyst. We know that metals. Gold nanoparticles coated titanium monolith. We prepare all those surfaces there and we used in the various reactions as well there too. Then I will show you that also the 3D printing zeolites, efficient CO2 absorbent, that has been made. That is the paper appeared in 2019 by China, that 3D printing's fabrication hierarchy, where the zeolites can also be used as a 3D printing materials, where the pellets, extruder, and then you can get the zeolite, this type of things as well. And then think about it. Now, the using as a pellets, using as extruders, now you are using a printed materials as zeolites. So that makes a difference, where the 3D printing come and using a zeolites in a different manners over there too. That can give you a great efficiency over there too. But what type of zeolites? It could be a sodium zeolite. It could be whether ZSM5 works out there. I mean, you have to read the paper. You will find out the full details in there as well. Then we start. There is another things come up, the catalyst functionalization of the 3D printing structures, where you can have the structures like that, and then you functionalize those things. You can not only functionalize the whole surface, but you can functionalize the selected surface on the surface. So you can surface of this middle one, then you can take the corner one. So you can have a combined effect of the different surfaces functionalize, and then can see the combined effect of any of the catalytic reactions. That has been done as well. In the, like, for example, synthesis of the customized 3D printing geolite monolith, and with the hierarchicals, micro, meso, macro porous structures, and after selectively towards the light olefins was favored, then you can do the certain reaction. You can find out which reaction works and which type of the doping you need is in there too. That can be done as well, is in there too. 3D printing reaction layers as well, that has been done as well, where you can see that you can prepare the as a reactor A, reactor design A. Now we are talking about the reactors. You can forming the different type of the reactors, and you find out the polymeric reactions, different type of the 80% yield, 90% yields. You can obvious there too. Again, this is a integrated 3D printing reaction layers for chemical synthesis and analysis. You can make those as well. This time the palladium carbon catalyst was deposited on the surface of the polymers, is in there too. Now the trick in all those reactions will be that how you can deposit those catalysts on those surfaces, how you can functionalize. That is the research area which is still left to be explored fully, is in there too. Sequential reactors, that you can mass those sequential reactors one after another, where you can join them, like a palladium carbon catalyst, silica columns. So you can join them, those reactors as well, to find out the combined effect of a complete process is there too. Suppose you want to have a reaction, product A, product B, product C. So you can make the product A in the one reactor, then product B, which is the precursor. The product A product will be the precursor of product B. So you can do all those reactions, all those possibilities, which were only possible when you start every time in new reactions is in there. That is a possibility. You have a combined reactors to get all those final products. So the 5-step synthesis, 4-step synthesis, which every step use a catalyst is possible by using this 3D printing reactor, the sequential reactors method as well. Then the functional catalyzed reactor has come as well, with the 3 kinds of the SCRs, the iron, cobalt, and nickel via the metal 3D printing technology. They have been prepared as well, as you can see that these things. You can use that, all those reactions. As you know, these metals are the catalytic active materials, and they can be used. You can make the catalytic functionalized catalyzed reactors itself, and then you can use, like, for example, self-catalytic reactors, liquid fuel, syngas. You can produce all those sort of thing as well. I mean, this is again, I will call it as a very novel concept, which is initiated from our previous concept, and this paper came from Japan and published for the Nature Communication is there too. Then the 3D printings, nickel alumina, that CO2 methanetions, where you want to convert carbon dioxide into the natural gas, or you want to convert dry reforming of methane, because the nickel and aluminum catalyst that can be used on the 3D printing materials as well. We can use the nickel and alumina, because the alumina is the surface where we can dope the nickel on top of it, and those nickel aluminum surface can be used as a catalyst for the dry reforming, or the CO2 methanations over there too.
Sorry,
then
Prof,
let me share with you that this is the things what we did. This is happening at my ends, where we created all these 3D printing metallic reactors, solid metallic reactors, with all the modeling has been done. All these has been tested, that how much gas flow they can take and everything's, all the efficiency of the methane burnings, So all those things can be achieved. These are the RMIT University, as I said to you, that we are made up there too. And this process, what we call as a DME methods, we use many of these reactor of the dimethyl ethers productions from the methanol economy. First, we make the methanol from the CO2 and CO2 dry reformings, and then after that, we make just the anhydrous reaction of the methanol, make the dimethyl ethers, which is a very good product, which very good fuels, and can be used into the cars without any much modification with the diesels. Is in there too.
Sorry, Prof.
And given that, then it is coming. Then I'm just about to finish in a minute. The hydrogen production demand is in there too. You can also use the 3D printing reactors of using that, and you can make the ammonia splittings, ammonia pyrolysis to the hydrogens, because hydrogen is commodity, and also you can use the methane into the hydrogen as well, is in there too. And that is the endothermic reactions, which I told you that is coming up in our chemical communications. I share with you, this is published today, this came out today only, so you can see. And that is the new concept is developing, that when we used a alloy metals there, and if you can dope in a special method zeolite on the surface, those metals from the alloy, from the metal surface, can migrate into the zeolite. Then you have a surface which is a metal exchange zeolites. And metal exchange zeolites has a variety of application. That is some things we proved first times in this chemical communication, which you can read probably. As I said to you, that is a time in there. And this, particularly in this reaction, we use these reactions to use the endothermics, because many of those chemical engineering reactions, or the fuel process where the supersonic flight goes up, the heating is a problem. It get heated. So we are using the cracking of the endothermic reactions, where this reaction can be act as a cooling effect of there too. That was the projects we did it successfully, and that is the outcome. And this is again is a start of the outcomes, I will say. Again, this is the mini DME projects. As I said to you, this has been gone to the commercializations, and the car, not only the car, but the production of the deuterated methanol is happening in the Institute of Petroleums over there, using these 3D reactor designings at RMIT over there. I would like to finish and would like to dedicate my whole lectures to my friends, which is no more with us. But I must say that without Professor Sharifa B, because I know those days when she put forward to me the concept of establishing a nanocat, the nanocat was not there. I'm proud to say that I'm associated with you from the day of the nanocat concept was initiated on these platforms. So I worked with her all the times. Probably many of you knows that too, but somehow she has no more with us. I mean, the life is always like that. So I would like to dedicate these lectures to late Professor Sharifa B. She was a visionary leader who made the difference. And I'm sure that University of Malaya and whole Catalysis community around the world will remember her forever. I would like to thank my collaborator. It's a big team, as I can say to you. And it is a chemic team, James, Kannan, Frank, Roxanne. She's a Belgium PhD student with me. At the moment, Ben is a mechanical engineer's PhDs. Carl Fogger, ex-chief scientist of CSIRO, is advisor. Milan Brandt is the director of the AMP centers. Machi is the AMP centers. Lakshmi Kentam, probably you heard for her as well. And Karen and Adams, they just joined about a few years ago to RMIT. And they are the part of the chemic as well. The other players are like the mechanical electronic engineers, Sam, and also the industrial chemist, the Elias. Jampa is a catalyst, and again is the material scientist of the Ahmed as well. So I would like to conclude my talks with these things. I hope you have something. It is a talk which I believe that probably required a lot more times to explain you everything, but I tried my level best to explain two things only here, that it is a time for 3-generation catalysis, and 3-generation catalysis is coming through the 3D printing. Thank you.
Thank you very much, Prof, for addressing this interesting topic on 3D printing. So now we come to the Q&A sessions. I'll read the questions from the Q&A panel. Yeah, the first questions come from Mr. Rika Rahman Nasaruddin. Dear Prof. Suresh, thank you for the interesting talk. Based on your experiences, may I know how to combine or incorporate metal nanoparticle or nanocatalyst into the 3D printed products? Is it only by coating? Is there any other techniques or method for that?
Okay, I think it's not an easy answer. There are twofold of the answers. Yes, it is by coatings. Coatings can be done, but the coatings can also cause not the stability of the nanoparticle on the surface. We are working on them, and we have established certain metals, and also it depends upon the a particular metal nanoparticles, because the interaction of that metals to the surface is very, very important. That's the one way. Second way of there too, that we are also developing the what I call the electrochemical methods, electrochemical modification of the surface. And after electrochemical modification of surface, we are creating a surface which are absorbing the certain nanoparticles in there. So depending upon that what nanoparticles you want to coat it on a particular surface, that these are two parameters you have to consider. The answer is yes, it can be done. but by choosing a variety of parameters.
Cool. Thank you, Prof. Another questions come from Dr. Malinda. Great sharing, Prof. Suresh. I wonder how do you maintain the homogeneity for the combinations of functionalized catalytic materials in the 3D printing?
Okay.
Yeah.
I think that's a good question. That question again, it depends upon the method you are using. It depends upon the method you are using. If you are using a electrochemical methods, yes, uniformity can be achieved without much problems, because then you dip the whole materials is there and the uniformity is there. Yes, you can do that as well. But and also chemically as well, if you dip the whole things. But it again depends upon the nanoparticles or the doping what you are doing it, and also what the surface you are using. Similar answer. Like suppose you are using incanol alloys. In this case, the latest paper we got it there. It has a chromium, it has a vanadiums, it has a aluminiums. So is a incanol alloys, and also it has iron, of course. So that once you are doping that, and once you are developing a methods of doping and centerings, is a combination of again parameters. You can see that how those particles either migrating coming up and how the surfaces are coming. Depending upon the nature of the surface, you can develop the homogeneity as well, isn't there? I mean, that is the area where the challenges are still there, but getting there. I mean, the results are coming quite nicely as well.
Yeah. Thank you, Prof. There are a lot of questions, but due to the time constraint, maybe we go to the last questions from Prof. Ong. Hi, Prof. Suresh, could you please share with us your successful path in commercializing technology and bringing new useful product to our society? Thank you.
Okay. Well, I think that's a very good comment, I will say. And we have used, as I said, that we have shown on a certain reaction pathways that the engineering and the science can work together simultaneously. And if we can optimize a catalyst by catalyst modification using 3D printings, the reactor designing using 3D printing is a lot easier, because that's engineering. That's just is a mechanical engineering combined with the chemical engineering, designings, and all those sort of things, modelings and everything. That's part of easy. So if you two combine together, certain manufacturing process are coming viable for sure, 100%. Many industries are now looking into it, and many industries you will find within 5 or 10 years will be working on the same concept.
Yeah, thank you very much, Prof, for addressing this interesting topic on 3D printing and answer all the questions. Yeah, once again, thank you, Prof. Suresh, for your sharing.
Thank you very much indeed.
You,
I'm really delighted to be part of your conference. Thank you.
Thank you, Prof. Yeah. So before we move along to our next keynote speaker, ladies and gentlemen, I'd like to seek for your kind cooperation to avoid any virtual disturbance during the sessions. For those who intend to ask questions to our honorable speaker, you can channel your questions in chat box. Your question will be raised in question panel, and I'll read it accordingly. Thank you. Okay, now moving along to our next keynote speaker, Associate Professor Dr. Rusinda Abdul Rahim. I'm pleased to give a brief introduction of Prof. Rusinda. Prof. Rusinda obtained her PhD in nanoscience and nanoengineering from Waseda University, Japan in 2012. Currently, she is a director of National Nanotechnology Center under Ministry of Science, Technology and Innovation, MOSTI, and associate prof at Institute of Nano-Electronic Engineering, UNIMAP. Her research interests include optimal development, electrochemical, nanoelectronics, nanocarbon, and nanobiosensor. Without further ado, I'm honored to invite Prof. Rusinda to share her topic today on the nanosafety, current and future scenario of nano-based industry in Malaysia. The stage is yours, Prof.
Thank you. Thank
Thank
you,
you.
Dr. Beverly. Let me share my screen. Can you see my screen?
Yeah, we can see now. Thank you, Prof.
All right. Thank you. Okay. Good day to all of you. And I'm Ruslinda from National Nanotechnology Center under Ministry of Science, Technology and Innovations. First of all, I would like to thanks for the organizer for having me today on sharing towards the nano safety current and future scenario of nano-based industry in Malaysia. United Nations Environment Programme under Strategic Approach to International Chemicals Management, it started in 2006. And the membership is include the governments, international governments, organizations, and non-governmental organizations. Nanotechnology and manufacturing nanomaterial listed as a strategic approach to international chemical management under emerging policy issue. And of course, the members have taken initiative to address the safety issues, such as the OECD established a working party on manufactured nanomaterials that meets annually. And of course, the ISO TC 229 under nanotechnologies via Working Group 3 on health, safety, and environmental aspect of nanotechnologies. And United Nations Institute for Training and Research introduced an e-learning course on nanomaterial safety. So before that, I would like to introduce that we do have a National Nanotechnology Policy and Strategy 2021-2030 that the foundation with this nanotechnology being an enabler towards Malaysia becoming a high-tech nation by 2030. The policy consists of 4 strategic thrusts, as you see on the screen, and also supported by 15 strategies and 32 initiatives. National Nanotechnology Center will coordinate, implement, and monitor the action plans and programs within the initiative. The strategic thrust 1, strengthening ecosystem and governance, the challenges that stood out was disconnected ecosystem in supporting the overall implementation, development, and innovative of nanotechnology. The 2 strategies will be put in place. The next strategic thrust, which is advancing research and development, it will guide the research, development, and commercialization and innovations of nanotechnology in the country, fostering the effective research partnership and collaboration among stakeholders, promote sharing of facility and infrastructures, and STEM education. And the strategic thrust 3, which is enhancing commercialization and energizing industry, address the linkages among key stakeholders, provide facilitations for nanotechnopreneur and startup, market demands for nanotechnology products and services, talent, and awareness. 5 strategies in this thrust will be supported by 11 initiatives. The next strategic thrust is the strategic thrust 4, strengthening standard safety and regulations. It consists of 3 strategies that to promote the importance of standard and safety towards increasing value of nanotechnology products, integrate into existing regulations, and re-strategize certification. It's supported by 5 initiatives, and one of it is developing a comprehensive nano database as an inventory of local nano-based product as well as reference on nano safety, standard, and regulation. Today, I will focus more on the strategic trust fund towards on the nano safety issue. For your information, we conducted a study to benchmark a risk-associated nano-based products in the local market. The studies are on the way and is expected to be completed by the year 2023. Malaysia is taking a slightly different approach from the developed countries. Instead of looking at nanomaterials or chemicals per se, our focus is on the nano-based products that reach the hands of consumer. The 5 scopes under this project, as you've seen on screen. And the first step is to establish an inventory of nano-based products available in local market. Study has been completed and will elaborate in the next few slides. And a selected products from the inventory will undergo nano-safety study. Series of testing comprises of physical chemical analysis, toxicology, ecotoxicology, environmental effect studies, and finally a product life cycle assessment. For a market study, for a start, Our inventory has a 400 local nano products. The information that comes with each product is its nanomaterial content, product applications, physical property, whether it is manufactured locally or imported, details on the company, and much more. 89% of the nanoproducts are manufactured locally, indicating that Malaysia is not merely a user of nanoproduct. The next is through the jump sector. We categorize the products into 4, as we call it as sectors name: energy and environment, wellness, medical and healthcare, electronic device and system, and food and agriculture. Almost half, of 49.5% to be exact, of those products in our inventory falls under the energy and environmental sector, followed by 30% in wellness, medical and healthcare, and so on. The trend may be shifting in years to come based on several factors, and one of it will be the current interest on R&D in nanotechnology, which seems to be skewed towards healthcare and electronics. The scenario will definitely change once those products can be commercialized and begin to enter our market. And another study in MICNC pipeline is looking at the nanotechnology products roadmap, where this document is expected to be published by year-end, and it will be very interesting to see how the market will adapt to new technologies and products. With respect on the region, the previous slide showed that 89% of products are being manufactured locally, and out of this, 75% of the factories are geographically located mainly in the central region of Peninsular Malaysia across 4 states. Why do we need this data? Well, basically, the nano safety is not only towards consumer, but also what will happen when it reaches the environment. If in the future, the concerns begin to be raised over the presence of nanomaterials in the environment, then we can immediately know the hotspots we should be eyeing into. So this is a living document, and the list will be regularly updated. And wish to note that this study was done during MCO, and the intended factory visits to physically verify the operations were limited to only a handful of manufacturers, and those in Sabah and Sarawak were not accounted for. We'll refresh the data from time to time, of course. And on top of that, by the types of the nanomaterials, when we look at the nanomaterial as claimed in those products, 35% is undisclosed. Information was gathered either from the company's website or product level, and 35% of the products claim to have nano, but is not indicated in its list of ingredients. This may sound alarming, but the study published by Marina and Bilstein Journal of Nanotechnology in 2015 showed that out of the 1,814 listed nano-based products from 622 companies across 32 countries, 49% did not disclose what are the nanomaterials in their product. A quick check in an online nano database showed that 70% of its 5,189 listed products did not disclose this information. What is lacking is awareness among manufacturers and suppliers, and also consumers, to start paying attention to what is in the products. Coming back to the chart, our inventory showed that the organic and inorganic nanomaterials are present in 18% of the products, followed by metal oxide 15%, polymer 11%, and so on. The organic and inorganic nanomaterials were included in 69 products, and the products in this organic nanomaterial listed as consumer as a food or health supplements, and the inorganic with application as coating material. Polymer nanomaterials in 43 products shows applications as high quality paint and also conductive coating on hybrid integrated circuit and printed circuit board house. The 15% metal oxide were recorded from a total of 59 products. The highest number was nanosilver, found present in 22 products with antimicrobial applications. Next were nanolid with 13 products, nanogold mainly in cosmetic with 10 products, and nanotitanium in construction materials with 8 products. The carbonaceous type of nanomaterial comprises of graphene in 16 products, carbon in 10, and carbon nanotubes in 4 products. Applications were mainly in the electronics, paint, and oil and gas industry. As mentioned earlier, for benchmarking reasons, several products were pre-assessed and selected for toxicology, ecotoxicity studies, and life cycle assessment. Physical chemical analysis will verify the products do contain nanomaterials. The basic methods include a dynamic light scattering, scanning and transmission electron microscope, and once confirmed, a series of tests provide data including pH, density, contact angle, circularity index, sphericity, zeta potential, and agglomerations and aggregations. Toxicology data will be all too familiar that we have acute oral toxicity, the skin or dermal toxicity into corrosion, irritation, and sensitization, comprising both in vitro and in vivo methods. Eye or ocular irritation using in vitro methods, inhalation toxicity, cytotoxicity, and genotoxicity, and further on. Ecotoxicity data includes dispersion stability studies using a recent OECD test guideline specifically for nanomaterials published in year 2017, the algae growth inhibition, Daphnia immobilization, and of course, fish acute toxicity studies using the zebrafish model, and all studies were conducted in compliance with OECD GLP. And the environmental fit studies look at a bioaccumulation and phototransmission. The present here on the screen is a safety data for completed nanosafety study on 2 selected products. Both products have received the NanoVerify certification. And first product is a coating material used to protect fabric and any adsorptive or porous materials from water and stain. The coating is invisible and does not alter surface color, texture, and appearance, but fabric remains breathable even after being coated, and main component is silicon. Second product on the right-hand side is a coating material used as tint for a variety of glass products. This tint provides shielding against harmful solar radiation as well as building insulated during cold or hot weather, and main component is sealant. So you can see here, these are the result that we identify through these 2 products by using the acute oral study, skin corrosion, skin irritation, eye irritation, chromosome aberration, and ecotoxicity. The next coming product is actually completed the LCA life cycle assessment on 2 selected products, which is the first product is a nano-based soil conditioner for activations of agrophysical and agrochemical processes in the soil, known as NanoGel. And assessment was conducted based on the cradle-to-gate life cycle assessment approach, which means the assessment was made on the ingredient acquisitions and production, including all transportation involved. The use and end of life of the product were not assessed due to data limitations, and of course, the direct linkage of the environmental impact of the product ingredients were non-existent due to the limitations of nanomaterial-specific background data. The second product has been explained earlier, which is assessment was also conducted on a cradle-to-gate life cycle assessment approach that we can see here. Those are the results obtained. We're now looking on the outcome of the project, which is a nano safety referral system. The output of this project will be compiled in a nano safety referral system. This online system is expected to be ready early next year. Having a product inventory is nothing new. In fact, such an information is also available online or elsewhere. You can readily look them up at StatNano and Nano database. And of course, the legislation is effective 1 January 2020. The export of nanomaterials defined as a nanoform into Europe will need to comply with the regulations established by European Chemicals Agency. And these are revised annexed within the registration, evaluation, authorization, and restrictions of chemicals, or better known as REACH regulations. And a quick update on the recent issues on titanium dioxide by the European Food Safety Authority. Mentioned here that the titanium dioxide with the code E171 contains at most 50% of particles in the nano range of less than 100 nanometers to which consumers may be exposed. Based on new scientific evidence and data on nanoparticles, EFSA has concluded that titanium dioxide can no longer be considered safe as food additive, but a critical element in reaching this conclusion is the genotoxicity concern after consumption of titanium dioxide particles cannot be excluded. After oral ingestion, although the absorption of titanium dioxide particle is low, but still they can accumulate in the body. Another issue that I would like to highlight is the nanosilver. European Commission is no longer approved nanosilver under the Biocidal Products Regulations or BPR for specific uses. Such a ruling will definitely be affected on products including disinfectants and algicides not intended direct application to human or animals, food and feed area disinfectants, fiber, leather, rubber, and polymerized materials preservatives. The EC database currently have 125 biocidal products and 66 or 53% of them are nanosilver. So what about our local regulations? So this table shows us that acts and regulations which may be affected when nanomaterials begin to show concerns, especially on its safety. And aside from occupational and consumer concern, the reaping effects will be seen in acts related to customs and transport. Specific labeling and new procedure will need to be put in place. And one particular act missing from this list is the Medical Device Act 2012 or Act 737. The Department of Occupational Health and Safety, DOSH, has published a guideline on control and safe handling of nanomaterial. This guideline takes the control banding approach similar to the handling of investigational new drugs. And coincidentally, Malaysia is leading a systematic review on the ISO TS 12901 document related to engineered nanomaterial, which uses the control banding approach in occupational risk management. From this study, NSC hopes to come up with more guidelines where we are already looking at Japan as an example, where government and industry takes a proactive approach in conducting joint studies on cellulose nanofiber. Subsequently, 3 documents were published in March 2020, which is on case study of detections and quantifications of CNF, procedure of safety tests on CNF, and also case study on emission and exposure assessment of CNF. So currently, the Department of Standard Malaysia maintains only one standard related to nanotechnology. The MS ISO TS 13830 was adopted from ISO with a similar number. This standard provides a guidance on voluntary labeling for consumer products containing manufactured nano objects. What we'd expect that our Malaysian Board of Technologies under MOSTI certifies technicians and professional technologists across 23 technology fields, and nanotechnology is one of them. And early this year, NNC has held discussion with MBOT to include a nanosafety as a recognized sub-technology field under nanotechnology. In supporting this initiative, NNC is in talks with a local training provider to organize a nanosafety course, which will offer CPD hours towards renewal of professional technologists and certified technician certificates. We foresee this course to be held annually, of course. And lastly, on the product certifications, Nano Verify is a very synonym with having a quality nano-based product. This product certification program will be elevated to be under the scheme for the accreditations of certification bodies conforming to ISO IEC 17065 to help secure and increase public confidence. And at present, these programs only verifies the presence of nano in products. However, NNC will assist to assure the safety is included in the next coming certification program. This was my final slide, and I would say that NLC welcomes discussion in helping us chart and implement nanotechnology programs and projects to contribute towards the Malaysian economy, and in this aspect, sustainability and safety of the nano products and services. Thank you for listening.
Thank you very much, Prof. Roslinda, for sharing this interesting topic on nano safety. Ladies and gentlemen, now we come to the Q&A sessions. I'll read the questions from the Q&A panel. The first question is from Dr. Tan Kin Han. Prof, good speech by you. May I know, is there any current rules, regulations about the use of nanomaterials that are being imposed in local research university? They seem like the policy, right? Yeah.
Thank you for the question. Yes, basically, we normally adopt whatever that the standard Malaysia have been used for the regulations. But of course, if we're starting, because this project is just starting and is going to be until 2023. So there's a lot more of things that will turns out towards the regulations. And of course, it will not be imposed with the local research university yet, but in the policy, we already aligned, we already, how do I say, we already write up what are the needs and taken need to be done to upon the regulation, especially for the manufacturing industry.
Thank you, Prof. And another questions from the audience. For the company or researcher who would like to contribute their product for the nano safety study or assessment, how should they proceed? Should they contact MICNC or CRIM? Yeah, thank you.
All right. For those industry who are interested or any researcher that have a product on towards a nano product that interested to be aligned with this study, you can contact me directly. Email me at ruslinda@mosti.gov.my. We will facilitate you and we will guide you for us to get your sample and to proceed under our studies as well. We are most welcome to having all you.
Thank you, Prof, for your sharing. Again, due to the time constraint, I think this will be the end of the session. And once again, thank you, Prof, for your sharing again. Thank you.
Welcome. Have a nice day.
You too. Have a nice day. So now we reach at the end of this session. Thank you for your participations. On behalf of MICNC 2021 Organizing Committee, I'd like to seek for your kind cooperation to fill out the feedback form as given by session moderator in the poll box. You are invited to join the next plenary and keynote session at 2 p.m. later. Hope to see you again after the lunch break. Thank you.
All right, good afternoon, everybody. Can you hear me? Okay, welcome back to our day one conference. I hope everyone have a good lunch. And this afternoon, we're going to have two sessions. We have one plenary talks, session 3, and also one keynote, session 2. After that, we are going to follow by our parallel session 1 at the later of the afternoons. And now it's 2 o'clock, so let's move on to our first presentations. So before we begin this afternoon's friendly reminder again, I would like to seek your kind cooperations to avoid any virtual disturbance during the live broadcast sessions. So if you still not familiar with the platform or you have any questions, kindly please refer to the conference resource personnel, which are ready to attend you at the reception desk. Just click there. Thank you for your kind cooperations. All right, good afternoon again, everyone. So we are now in the plenary sessions 3. My name is Ong. I'm from Nanotechnology, University Malaysia. We'll be chairing this afternoon sessions. So before we started, it's a great honor that we have two very distinguished scientists going to share with us on their latest works. One is on the machine learning, and the other one is on the electrocatalysis, which is going to take 1.5 hours before we move on to the parallel sessions. So let's begin with my honors that we invite Professor Amanda. I'll go through, he has a very long and impressive series. I'll go through briefly to introduce Professor Amanda Burnett to everyone. She's one of the Australian most highly awarded computational scientists. She graduated both her BScs in applied physics and also PhD in theoretical condensed matter physics from RMIT University, Australia. After graduating, she received distinguished postdoc fellowships in the Center of Nanoscale Materials at Argonne National Laboratory, USA, and also the prestigious senior research position as Wallace and Samuel Grafstone's Fellows at the University of Oxford, UK. She won a lot of awards, and I just name a few that she received recently. In year 2014, Professor Amanda is ACS Nano Lecturerships, Asian Pacific from the American Chemical Societies, and also at the same year, the famous prize in nanotechnologies theories from the Forsyth Institutes. And the most recent one in 2019 is AMMA medals from the Associations of Molecular Modelers of Australia, Asians. So without further ado, please join me to welcome Professors Dr. Amanda Barnett on her talks titles Structures, Properties, and Property Structures, Relationships of Nanoparticle Catalysis from Machine Learning. The floor is yours, Professor Amanda.
Thank you. Thank you so much for that wonderful introduction. My only regret is that I couldn't be with you in person. The island looks beautiful, and I've never been to Malaysia, so I was really looking forward to it. But I'm glad to have the opportunity to give you a virtual presentation today. Today, I will be presenting some work done by my students, Sicho Lee and John Ting, and I'd like to start by acknowledging their important contribution to what you'll see today. I'll talk to you, as mentioned, about structure property, but also property structure relationships that we can get from machine learning. My area is computational science, and I'm the head of computational science at ANU. And overall, computational science aims to use mathematical models to solve computationally demanding problems in all areas of science and engineering, and to find technologies in computer science that can enable us to solve these problems on a very large scale. So we use a lot of supercomputer simulations. We also use advanced computer science techniques such as machine learning and artificial intelligence. And the idea here is that we can enable new approaches to a cross-disciplinary area of science by effectively being able to utilize the new technologies that computer scientists are inventing every day. As computational scientists, we collaborate widely with lots of different areas of science, including environmental science and biology, chemistry, medicine, astronomy, and nanotechnology is one of the most exciting areas of opportunity for us. So the work I'll show you today utilizes both high-performance supercomputing, machine learning, and nanotechnology to see if we can help solve some problems in catalysis. The work that we do captures both the simulation and informatics tools that is part of the scientific method, the scientific method repertoire that we have to apply to all of our big challenging problems. This complements the areas of experiment and theory that have been used for millennia. There are some intrinsic differences to these different types of approaches that it's interesting to see how they can fit together. Both experiment and simulation, one of course in the real world and one in the virtual world, are observational methods. They gather information or data, in the case of simulation capture, to help us deduce more about the world around us. They are by their very nature explanatory. They help us explain either a real or a virtual observation. In contrast, theory and informatics are hypothetical. They use information to impart knowledge. They are inductive, and by their very nature, they're exploratory because they allow us to try to understand something new about things that we can't observe. They allow us to, if they are sufficiently complex, to interpret the world around us, to interpret the data, and to do data-driven or capture-driven investigations of things, for patterns in the data or capture that we can't naturally observe and is too complex for humans to understand. Both of these two methods that we use in computational science, simulation and informatics, they both are on a computer, but they are fundamentally different in many ways. Simulations, which we're probably much more familiar with over many, many years of scientific literature, and perhaps our own collaborations, is a bottom-up approach. We start with some underlying question, we gather our information, and then we impart some new knowledge about the system. Informatics is exactly the opposite. Informatics is a top-down. We start with all of the data already, and then use our informatics and machine learning approaches to give us some new understanding of the fundamental question. Simulation is based on rules. This comes from the science. Informatics is based on experiences or history. Simulation is largely based on deterministic methods, whereas informatics is largely stochastic. One of the great advantages of having a deterministic model in a simulation is that it enables us to extrapolate. In contrast to that, informatics enables us to actually interpolate into the space in between the data that we have. One of the greatest differences between these two approaches is that they use a completely different kind of logic. Simulation is based on an if-then-self logic. If I put in a certain number of input configurations, then I will get a certain answer, else, well, the software was probably going to crash. Informatics, in contrast, will always give you an answer. It just may not be a good answer. It relies on an estimate, improve, repeat logic. So the more times that we repeat the process, the more we improve the outcome. But it's unlikely to ever give us no outcome. It's unlikely to crash. And of course, the very compelling difference between the two is that simulation, because it's based on the rules of science, it intrinsically relies on human intelligence, whereas informatics relies on artificial intelligence. Artificial intelligence captures a range of different kinds of tasks, intellectual tasks, that we also as humans are able to do. This is just a short list, but it includes perception, representation, language, learning, optimization, and planning. Today, we're going to think mostly about machine learning, the learning task, where effectively machine learning enables a computer to program itself. Before the advent of machine learning in the 1950s and 60s, scientists had to have a very good understanding of the problem and even an idea of the solution before they were able to formulate the model. With the advent of machine learning, the machine is able to formulate the structure of the solution and the model at the same time. And this has, of course, been able to accelerate discovery in a range of different areas. In contrast to this, human intelligence, also known as domain knowledge, has a number of important aspects that AI doesn't have, which we want to retain in any kind of scientific investigation. This includes our ability to be creative and think outside the box. It includes our ability to be subjective and make qualitative judgments that are not simply based on the numbers. Humans have the ability to be generous, to make trade-offs between different kinds of decisions, and to be practical and think about what equipment we have in the lab, how much we can afford to do in the lab, and how long things will take. We have an amazing appetite for taking on risk and a willingness to try, even if the data doesn't support that it might be a good idea. And we have personal preferences to ignore advice when it suits us. And most importantly, humans have the ability to make mistakes and learn from them, which is something AI can't do. So a more holistic approach to a scientific discovery in any field, but particularly in catalysis and nanotechnology, I've found, is to find a way to bring together AI and HI, human intelligence, together rather than relying on only one of them. And this is definitely an area of our own research where we're trying to find ways to bring together these two aspects so that we can have the benefits of both. Unfortunately, the humans are not all good. We are also the biggest source of bias. All the decisions we make at the very beginning of the study or during a scientific study can introduce bias into the system. Examples include selection bias, where we'll only gather subsets of samples. So this is where we restrict our experiments to only certain experiments that we think are going to be meaningful. We introduce evaluation bias, and this is where we restrict the model to only certain features. This happens when often we've only got certain types of equipment available in the lab, and so we can only characterize our nanoparticles in certain ways. We introduce information bias because, as we know, mostly in the lab, there's a bit of variation from batch to batch or scientist to scientist, or perhaps we get a different answer on a different day. We introduce confidence bias because we're very confident from reading the literature that we know how to correctly characterize the properties of our systems. And sometimes we're open to misinterpretation. We're actually a lot worse than the general population in that regard, researchers, that is. We sometimes fall victim to attribution bias, assuming that if there's a correlation or a relationship between variables, then this means that there's a causal relationship. And confirmation bias, when we focus the results on only things that support our hypotheses. This might be, for example, if we were to gather data about nanoparticles of different sizes, when we were looking for a size-dependent relationship. Of course, we're going to get that. We've confirmed it from the outset by only collecting the data that confirms that hypothesis. Evaluation bias is another one where we default to familiar assumptions, usually based on what we've read in the scientific literature, and reporting bias, where we deliberately look for those very perfect and wonderful results that are most likely to get on the cover of Science or Nature and report those ones in our papers. So all of these sources of bias is something that if we consider in the future that we're going to want to use a machine learning approach, we should seek to try to eliminate them at the outset, or at the very least, recognize that they're there, and look for data science solutions that can help us to overcome them. We also suffer from a number of numerical challenges. Most of the machine learning models we want to use were never intended to be used for the kind of data sets we have in nanotechnology or in the physical sciences in general. Our data sets tend to be very small, and most machine learning models were made with the intention of working with data sets that are very large. Our data sets tend to be very high dimensional in the feature space, which means we tend to compensate for the fact that we don't have very many data samples by doing a lot of characterization. The features we have are also of different dimensions. We have counts, we have volumes, we have surface areas. We also have high variance between our features and often dependent measurement uncertainties. Our data sets are almost always nonlinear and imbalanced. Our data often comes from different sources too. These are all these different instruments that we have in our laboratories or different kinds of software that we use to generate and characterize them. Not every single one of our experiments works, so we often have missing data. And we, in the physical sciences and also in other natural sciences as well, are one of the few areas machine learning encounters where we expect that our data may actually evolve and change over time. These numerical challenges can also be addressed using data science methods, but once again, we only know to address them if we've characterized our data set and we understand that some of these problems and challenges are likely to be there. Once we've eliminated our bias, thought about our data science to overcome some of these challenges, then it's up to us to then choose the machine learning method that's most suitable. There are literally hundreds of different machine learning methods out there. Some of them do similar things and some of them do very, very different things. There is no superior machine learning method that is good for all problems. They were all developed with a very specific problem in mind, and those specific challenges they were developed for are all different. The choice in choosing a machine learning model for the kinds of science challenges we work on in materials, physics, chemistry, and biology should first and foremost be informed, of course, by the science question we're trying to answer. But we also need to think of the nature of the problem, whether it's a pattern recognition problem that we should use in unsupervised learning, or whether we're trying to predict a continuous or discrete label, such as the class of a nanoparticle, or its catalytic activity under certain conditions. This requires supervised learning. Both of those methods will be looking at similarity in patterns and correlations, but in some cases we want an actual causal relationship and understanding how our impacts are actually driving our outcomes. And for that, we need statistical learning methods such as inference. The characteristics of the dataset, as I just mentioned on the last slide, also play an important part in us deciding what method to use, as do the goals of our study. Do we need our results to be interpretable? Is a black box such as a neural network sufficient to just give us a prediction? Or do we need more of an understanding of why we get a certain answer? Machine learning models also, depending upon the method, can take a lot of computational resources to run. It's often assumed that they're going to be faster than a simulation, but some machine learning methods take an enormous amount of resources and require very powerful GPUs. So thinking about the practical considerations of what we can actually do in our own research is another important factor. And finally, that list of bias that I mentioned. Some methods are even worse at amplifying biases. So if we feel that there might be bias in our system, then the right choice of method can help us to compensate for that. Today, I'll talk through a case study that uses machine learning and has to think about a lot of these issues, trying to answer one question in nanotechnology and catalysis. Can we use machine learning to predict the structural characteristics of a metal nanoparticle that will deliver a very specific set of catalytic properties? So basically, we've got the properties in mind and we want it to tell us what the structure that we should be making in the lab will be. We'll be using a synthetic, that's a computational data set generated using molecular dynamics simulations, and we'll be using indicators of catalytic performance based on a statistical characterization of the features. We'll then be applying machine learning to predict not just a structure-property relationship, a forward relationship, where we know the structure and we predict a property, but also a property-structure relationship, where we know the properties we want, and we want it to predict the structure we should make. We'll then train these models, and this will give us the ability to actually predict a recipe of what we can make in the lab. The data set is a set of platinum nanoparticles, which is freely available to download for anyone to try at home, generated using molecular dynamics under different kinds of temperature and atomic rate deposition conditions. So different growth rates, different growth temperatures, and grown for different times. As we can see here from the little examples I've shown to the left, the diversity within this data set can reflect a number of different types of nanoparticles that we would see experimentally. They can range from a perfect, nice, neat little zonahedron or a polyhedron shown there at the upper left. So we can contain surface defects, which we know can impact catalytic activity. It could be a real spherical particle that does have some surface faceting and ordering, or it can be a completely disordered particle which has branching, surface roughness, and quite a lot of structural diversity. The set actually contains 1,300 individual nanoparticles that range in size from 54 to just over almost 16,000 atoms. So there are different sizes and shapes and imperfect structures present. To characterize the structure for the feature space, we've used 3 different descriptors. The first descriptor is an atomistic descriptor, and this includes features including the interatomic coordination numbers, the fraction of surface atoms, either in the bulk or on the surface, things like bond lengths, bond angles, everything to do with interatomic relationships. The second is a topological descriptor, and this is something unique to nanoparticles that you don't see in materials informatics. This includes things like size, the shape, the types of surface facets or surface curvature, and if we've got a non-crystalline one, such as the ones shown at the bottom on the left, the types of anisotropy that might be present. And finally, we also capture a crystallographic descriptor, and this includes features including order parameters, the fraction of face center cubic or hexagonal close packed, the amount of disorder internally and on the surface. And so we end up with a total of 121 manually extracted features that require us to then do our cleaning and processing. So our data set is 1,300 instances, and it's 121 dimensional space. One of the things that we have to do during our data cleaning is to remove strongly correlated features. There's lots of different data cleaning involved, but this is one example showing a correlation matrix here. The very bright regions show areas where particular features are strongly correlated. We need to remove these from the machine learning model because if there's 2 features that are strongly correlated, they don't give us 2 bits of information. They only give us 1 bit of information. Removing the other one removes that redundancy and improves the performance of the model, making it run faster and meaning that it doesn't have to try to fit to noise. We also remove low variance features and outliers and clean the data set for some of the numerical problems around potential nonlinearity and imbalance. When it comes to the property, we also need to characterize the nanoparticles for its properties. And in this case, we're going to use indicators of catalytic potential as the property labels based on a survey of experimental literature. So this process in machine learning is referred to as labeling. And labeling is one of the most time-consuming parts of any machine learning study. In this case, we've labeled the nanoparticles by the proportion of surface atoms with different ranges of surface coordination numbers. If the surface coordination number is between 1 and 3, this is the top, bridge, and hollow configurations, then we know from the literature that these atoms are likely to be linked to carbon monoxide oxidation reactions. For atoms on the surface with a coordination number of 4 to 7, these ones are termed surface microstructures. This involves things like kinks and steps on the surface, and we know from the literature that these are likely to catalyze oxidation reduction, oxygen reduction reactions. Surface coordination numbers of 8 to 11 have been grouped together, we termed as surface facets. These are quite flat regions, regardless of what kind of facet orientation they are. In the literature, these have been shown to be catalyzing hydrogen evolution reactions or hydrogen oxidation reactions. We also include another label, the formation energy, as a measure of the overall stability. So this gives us, in our 1,300 instances, 121 feature space, dimensional feature space, and 4 property labels. Here's the distribution of those 4 labels. For the most part, you can see that the surface microstructures, surface facets, and formation energy have a largely Gaussian distribution. Most machine learning methods were designed to work with Gaussian distributions. And so even though we have a slightly bimodal distribution in the case of the formation energy, accounting for the particles that are very disordered or very ordered, overall these distributions won't be a problem for almost all machine learning methods. And in each case, we can show the test-train split. This has been done in a stratified way, which means that we've ensured that the distribution of the testing set is the same as the distribution of the training set. This is particularly important for the surface defects shown in the upper left, which are interesting for their potential for carbon monoxide oxidation reactions. In this case, we can see there is a lot of imbalance. This is significant imbalance that poses a very severe problem for almost all machine learning methods. We've applied stratification, and you can see that the distribution of the pink test set is the same as the training set. But however, we don't expect to get very good results for this label. The method that we're going to use in this case was informed by, obviously, we want to have a good representation of the relationships between the structural characteristics and the property labels. But we also want an interpretable method. So we've chosen to use decision trees. Decision trees predict the value of a label, in each case, any one of our 4, following a set of decision rules that it infers from our high-dimensional feature space. We can also collect them together to use in the form of a random forest, which is an ensemble technique based on collection of a large number of decision trees and a bagging or bootstrap aggregating method, which randomly samples the training set with replacement. Each node on an individual tree splits based on a decision at the node, but across the entire random forest, each tree then uses a random distribution of our features, and then the decisions for the individual trees are then counted using a random voting system at the end. The features are then ranked during the training based on variance reduction during the regression tasks to avoid overfitting. So that's a lot of machine learning talk there, but the main advantages for us in thinking about our nanotechnology and catalytic problem is that these models are nonlinear, because we know from looking at our distribution of our labels, we have nonlinearity. They're non-parametric, which means we can use them for lots of different distributions in our labels, and it doesn't pre-prescribe the structure of our model. They're also interpretable, which means that not only do we get an answer as to what a property structure or structure-property relationship will be, but we also get an indication of how important different characteristics of the nanoparticle are in the formation of these decisions. So here's some results using a random forest just to do a single target structure-property relation prediction. This is the kind of prediction you'll often see in the literature that uses machine learning for nanoparticles. We've standardized and normalized the features and labels and eliminated outliers, and we've removed features with over 95% correlation. So that's some of our cleaning and preparation of the data. We've then done a 25-75 test train split with 10-fold cross-validation and random hyperparameter optimization. We've evaluated here using the mean absolute error and the mean squared error. And for each one of these forward models, after the cleaning, we've retained 37 features. So the cleaning process, removing strongly correlated features, actually reduced our feature space from 121 down to 37. In each case, the forward model, using these structural features to predict each one of these different target labels, has given us an exceptionally high-performing models, but there is some variation. Because these results have been standardized and normalized, this is effectively just over 1% of an uncertainty or error in the prediction of the formation energy. As we move down to the surface defects, we can also see there for these reactions, the model performance is worse. It's actually 2 times worse. The model overall performs quite well, but still we can see that there's a variation in performance. So we're confident that the random forest can do a good job, particularly given we were expecting there to be some problems with surface defects. Here is going through these results and understanding how these fits are interpreted. So here's the results for the stability, the formation energy, and we can see here the blue line almost perfectly overlaps with our perfect fit. And even though there's some scatter here, the data is very well aligned. It's an excellent result from machine learning. The feature importance profile tells us, in forming this decision, the most important characteristics of the nanoparticle are the maximum radius, the ratio of surface to volume atoms, and to a lesser degree things like the coordination number or average bond angle, which tells us a bit about whether it's ordered or disordered. The surface facets, we can also see that the blue line almost overlaps perfectly with the perfect fit line, and we still have a bit of scatter, but an excellent machine learning result. The feature importance profile in this case says that the most important characteristics in determining hydrogen evolution or hydrogen oxidation reactions are likely to be about curvature of the surface atoms, in this case, small curvature, so as flat as possible, the average bond angle, and the average coordination number, which are related to the degree of disorder or order. So we have flat surfaces and how much order or disorder are present are the most important characteristics in these types of reactions. Surface microstructures, we also have a good result, some scatter, but a good agreement between the best fit and perfect fit, and then a different feature importance profile again. Here it's the surface curvature, but actually curvature where we see surface roughening, between 20 and 40 degrees of surface roughening. And the coordination number, average coordination number, is also highly important, which tells us a bit about the disorder. We also see here that the surface to volume ratio is important as well, and also things such as the maximum radius or the standard deviation in the radius, which means unlike surface facets, the previous one for hydrogen evolution and oxidation reactions, oxygen reduction reactions are also size and roughness dependent. And the surface defects where we didn't expect to get good results. And here we can see why. Because of this imbalance and the problems we had associated with it, the best fit line is not in good agreement with the perfect fit. And so that good score that we got is rather deceptive, because we can also see that there is a lot of scatter from the data, and the data sets are not well aligned onto the perfect fit. The feature importance profile also indicates that something's definitely amiss here. It indicates that the surface defects, the entire model is almost 100% dependent on the curvature between 60 and 70 degrees. So this is very strongly correlated to the top, bridge and hollow configuration of surface atoms, but it's largely ignored everything else about the nanoparticle, with almost no importance placed on anything else. We can also see that the level of importance on the remaining features is roughly the same, which means also it is treating everything else about the nanoparticle as noise. One great advantage, however, of using a random forest is it enables us to do multi-target learning. This means that instead of individually predicting each one of these property labels, we could actually predict them all at the same time. This means we can build a model that allows us to make trade-offs. So what if we wanted to know what features are important for both hydrogen evolution and oxidation reduction reactions, or if we wanted to suppress one and promote another? We need a multi-target model in order to do that. Random forests are one of the few machine learning methods that allow us to fit to more than one target label simultaneously. We simply substitute the univariate trees for multivariate trees, where the leaf nodes refer to more than one target label. And when we do the sampling across the ensemble, then we take into account the different labels, as well as the different sets of randomly chosen features. Here's the results for a multi-target model. It's very difficult to do one of those 45-degree plots because we're predicting lots of things at once. If we look at the feature importance profile, we can see that the surface to volume ratio is important, of course related to the size. Having flat surfaces on the surface, flat facets, is also important. The average radius and some features here related to degree of order and disorder. So that is kind of a mixture of the ones that we saw in the individual single target cases, so it's not surprising. We can also see that there's a very strong decay, and most of the features of the nanoparticle are not used at all. Recursive feature elimination using 5-fold cross-validation shows that actually we can get an optimal result with only 24 features. So this means for our multi-target learning, we can reduce down from 37 to 24 and even simplify our models, removing some of these nuisance variables that are not adding any information. So when we add the multi-target results here as well, using all 37 features, we have lost some degree of performance in the model compared to the single target results, but we're still talking about only 2% of a loss. When we reduce them even more to just the 24 most important features identified using the random forest feature importance profile, we are able to improve the performance a bit. We're looking here at around 2% of uncertainty, being able to predict all of these models at the same time, which is a very good outcome. What we really want, however, is not just structure-property relationships, because they're very insightful and it's very interesting to understand these relationships, but we can't act upon them. We need a property-structure relationship to be actionable. It's necessary to have something that's actionable if we want to design catalysts with specific functionality that we can use as a recipe to translate from the lab into industry. Conventional approaches in the literature to inverse design is to use a forward model, just like the ones that we've predicted previously here, and predict all of the properties we would expect for a hypothetical set of different materials, and then use another algorithm, a global searching algorithm, such as the genetic algorithm, to then rank them against some different kind of selection criteria. The problem with this approach is that it can only find materials that are in the list, and if your list isn't exhaustive up to Avogadro's number of possible configurations, you could miss some. It requires an additional algorithm that also comes with some overhead and additional uncertainties related to it, relating to the genetic algorithm, for example. It can predict materials that are not stable and you can't even make. It can also predict more than one material that has, or nanoparticle, that has exactly the same properties, which means that you can't just have one recipe. There's some ambiguity there. And this is because it's mathematically impossible to predict multiple unknowns from only one known. So if you only have one property that you're trying to optimize against, then there's no way you can solve for many, many different structural characteristics. But we're using multi-target learning, and we have multiple properties that we're considering. So using multi-target learning, we can actually have a different approach to inverse design. We can invert the model, the kind of model that we've already used. And because we have more knowns, we can solve for many more unknowns. The structural features become meta-labels and the properties become meta-features. What we're looking at here in the workflow diagram on the right, which looks very complicated, is in the first column, towards the left of the diagram, this is our normal machine learning approach that I've just shown. We collected our data and labeled it. We did our data cleaning. We then split into testing and training and validation sets. We optimized our random forest model and then did the training. We then came up with a feature importance ranking and understood which important features we have. And when we double checked that and ran the model again with only 24 features, we checked to see if we had any loss of performance. But what we want to do now is to take these important features at the bottom of the left column, invert them, and then in reverse, run the same multi-target machine learning approach using meta-features and meta-labels, where we also have a training and a test and validation set. We optimize a random forest. We also fit the inverse model and enables us to do inverse design. This avoids the need for an external algorithm for optimization, global searching. It can use small and limited data sets, And the best thing is it can identify candidates that were not already in the training set. So we don't need to have an exhaustive data set in order to do this. It also means that we can take advantage and benefits from the forward model and only concentrate on the most important features that we're likely to get a high-performing result, things that we can actually action and use in the lab. So let's compare the results. Here we've got results of the forward and inverse design. So at the top row in this column, in this table, we have the forward results for all of our 37, looking at all of the properties simultaneously, and we've already seen just over 2% of a means absolute error. Our forward model with 24 features, once we identified which ones were important, predicting all 4 properties at once, gave us an improved result. The inverse model then uses those 4 properties to predict the 24 most important structural characteristics. And we receive a model which, even though we're trying to predict 24 unknowns with only 4 knowns, our mean absolute error is only just over 5%. So we have a remarkably good result in doing an inverse design, predicting 24 unknowns from 4 knowns. The insights that we can get from a model that is capable of doing this can be quite useful and profound. The inverse model then, if we take a set of property indicators that we want to try to create, we can use this model to directly predict what structural characteristics would be required. So if we have no surface defects, 33% of surface microstructures, 34% surface facets, and a formation energy of around 0.38, 38% between 0 and 1, then this model predicts that we should make a particle with a maximum radius of just 26 angstroms, that we should suppress the surface, the 110 surface area to less than 4%. The fraction of FCC atoms that we would need to encourage the nanoparticle to have is around 50%. So we have a tolerance there for quite a lot, for these particular properties, a tolerance for quite a lot of disorder. When we look at the agreement here between the true value and the predicted value, we can see an excellent fit compared to the perfect fit, and the scatter of all of these different structural characteristics is very close to the perfect line. So we can have confidence in all of the different structural characteristics that this inverse design model will predict once we input what properties we want. But what about the human knowledge? What about all our expertise and experience? What about the human intelligence? So in many cases, as researchers, we have all of those other issues we need to consider, such as practicality or an ability to try something new and the willingness to make a mistake. So what if we made some interventions on that feature space and the 24 most important features that the machine learning predicted that we should focus on? Let's, for example, say, what if we made a new set and focused on just the structural features? And so we weren't so much worried about things like the growth rate or the temperature. In this case, that change represents a change of 4% of the feature space in the model, 4% of our human intelligence domain-driven features. Alternatively, we might want to concentrate only on features that we believe we can actually control in either a simulation or experiment. And so if we removed any of the features from that list of 24 that we didn't feel that we had a good control over, then that means we've made a change of 42% of the feature space. But these are reasonable considerations for the practical things that we need to consider in the lab. If we were to do this, then the new inverse model shown at the bottom here for the structural and controllable sets actually show a very similar performance to the top 24 features that the machine learning predicted to focus on. So by making a small change and only looking at structural features, we actually have an increase in performance. By focusing only on the ones that we feel confident we can control, we've lost a little bit of performance there, a slightly larger mean absolute error, but still less than 6%. This type of approach to inverse design has quite a bit of tolerance for us to start introducing some of our domain knowledge and preference. Here's the results for, say, the structural set, where we're only looking at features related to the structure of the particle for exactly the same types of properties, we can see that the maximum radius slightly smaller, but around 25 angstroms. The amount of tolerance for the surface area in the 110 direction is also just less than 3%, as it was before. And the fraction of FCC atoms we should have is about just under 50%. So that hasn't changed very much. So we still basically have, for the same properties, pretty much the same prediction on the same recipe, even though we've made a bit of a change to the model. For the controllable set, where we made a 42% of change to the feature space included in the model for exactly the same properties that we might want to have, we have basically the same maximum radius, only 3% of 110 surface area, and around 50% of FCC. So this means that, again, even up to 42% of an intervention and change on the feature space, 42% of disregarding what the machine learning said and introducing our own human intelligence, we can see here still have very good agreement between the true value and the predicted value. So this multi-target approach to inverse design can actually accommodate quite a lot of our human intelligence and still give us reliable results. But what if we wanted to ignore the machine learning entirely? What if we wanted to say, I know better what I want the model to do. I have very specific requirements in my lab that I need to fulfill. If we wanted to have entirely domain-driven features rather than data-driven and ignore that important feature importance profile that gave us the top 24, we could have a feature space called experimental. This focuses on the kinds of features that we are confident that we can measure or manipulate using microanalysis, or processing, where we only focus on things such as the growth rate, the growth temperature, or the growth time, so the things that we would use during synthesis. In this case, we can see from the two at lower rows in this table, this makes a significant change to model performance. The experimental feature space, where we're using our 4 properties to predict 8 experimentally accessible features, has increased the mean absolute error to nearly 7%. And in the case of the processing, where we only focus on inputs into the synthesis of the nanoparticles, we actually have a better ratio of predicting using 4 properties to predict only 3 processing conditions, but our mean absolute error has increased to around 10%. So looking at the actual model predictions from this experimental set, again, we have exactly the same properties, 100% user-specified domain-driven features. Our radius is a bit larger than it was before, around 30 angstroms for our maximum radius. The value that we get for this, in this case, the 100 surface, because the 110 surface was a data-driven, not a domain-driven feature, means that we actually can't predict the one we had before. And in this case, we're predicting an entirely different type of surface facet. The amount of FCC that we can tolerate is a bit lower than it was before, around 46% instead of around 50%. But looking here at the comparison between the true and predicted value, we start to see a deviation of that perfect fit of the model from the best fit of the model from the perfect fit. We're starting to see a deviation and an impact of our manipulation of the feature space based on our domain knowledge. And finally, if we were to focus on just on processing conditions for exactly the same properties that we might be interested in, here we can only predict, of course, the temperature, the time, and the growth rate. But the telling result is here in this 45-degree plot, where we can compare the true value and the predicted value, and we can see there's no longer any agreement between the best fit our model can produce and the perfect fit that we need. So in this case, by changing the feature space, we no longer have a reliable model at all. Unfortunately, once we get up to 100% user-specified changes and domain knowledge in the feature space, ignoring all of the data-driven model parameters, unfortunately, we can no longer reliably predict what nanoparticle we should be making in the lab. So in summary, using multi-target inverse design, we have a model that can give similar performance to a single target structure-property relationship, but we're capable of predicting multiple properties simultaneously. This multi-target model can be improved if we focus specifically on the feature selection used by using machine learning feature importance profiles. The inverse property structure models can also be developed using multi-target learning based on sets of properties, and we can confidently predict exactly what kind of nanoparticle we should make. And the inverse property structure performance, however, decreases the more we start to make our own domain knowledge changes and introduce more human intelligence into it. We cannot predict variables that are found to be unimportant in the associated structure property relationship. In terms of catalysis, what does this mean? Well, it means now we have an approach that can predict specific structural requirements based on a set of properties. The structural characteristics are more reliable than processing conditions. The size and the amount of flat surfaces is one of the most important things, no matter what reaction you're interested in. And we can use exactly the same approach that I've shown here for other catalysts and for other types of reactions. So with that, I'll thank you very much for your attention. Acknowledge once again the contributions of Sicho Lee and John Ting in the work I've shown you, and the contributions from some of my previous group members in preparing the data set and the underlying methodologies. Thank you very much.
Thank you very much, Professor Amanda, for your very interesting sharings. We have a list of questions over here. Maybe we'll start with the first one by Dr. Laili. Okay, dear professors, machine learning may be applied to the productions of nanoparticles, which involve a multi-stage reactions and separation procedures. What is the best way to obtain the best response conditions?
That's a very good question. So whenever we have a series of processes that are involved in the labs, this often would lead to us needing to have a series of different machine learning methods that can be used in concert. So there are a couple of approaches. We could start off with a much more comprehensive feature space and then apply a series of models. We could apply instead models that are based on things like reinforcement learning that include information about the environment and allow us to generate a time series of events. And we could also use statistical learning methods such as Bayesian inference. And Bayesian inference gives us a causal relationship of actually a chain of events and how they relate to the other. So this would allow you to be able to connect one process to the next process and finally to the end result.
Great. Amanda, just want to get a sense of the thing that you shared just now. Typically take how long if from the sketch I want to start something like this?
How long does it take? Well, okay. Yep. So I think it depends on how much knowledge you already have of the methods. So I have most of my students, well, all of my students come from a computer science background. So that means they're already very familiar with the computational methods involved, and it enables them to make progress very quickly while they're learning about the chemistry and the catalysis and the nanotechnology. In the past, I have had students and staff that have come from a nanotechnology background, and certainly over the period of a PhD or a postdoc, they can very easily learn what they need to be a very productive employee in the future. But it is a little bit slower because they need to come up to speed with the programming, with the mathematics, and with the machine learning before they can actually start to make progress. So depending upon what your background is, it could be a fast process or it could be a slow process to start getting to results. But I'll tell you the fastest way, collaborate. That's the fastest way to start generating new predictions that you can use.
Cool. Thank you. Let's move on to the next questions. It is possible to use machine learning to predict the interactions of nanoparticles with cellular proteins. Is it similar to docking study in this case?
You could certainly use a similar approach used in computational biology to look at docking. You could combine that kind of approach with some very interesting machine learning that could help speed it along. So in a docking study, then it's literally a brute force approach of taking a molecule and finding what its interaction is in different parts of a protein. We can imagine that is also a nanoparticle on a protein or something attaching to a nanoparticle. In order to get a complete holistic approach to all of the docking possibilities, pharma companies normally do a very exhaustive docking study. But we could improve that and speed it up using machine learning, using a type of machine learning called active learning. With active learning, we start to sample the space of the interaction. And as the model starts to get more and more confident in being able to predict it, it can recommend exactly what new data points that you need to gather. So it starts to tell you what experiments to run or what simulations to run. And it tells you when you stop. It tells you when it's had enough, it's got all the data it needs, and it can predict all the things that you haven't done. So this means that instead of needing to sample thousands or tens of thousands of interactions, you might only need a few hundred, and it'll tell you the exact right 100.
Yeah, thank you for the excellent answers. And thank you for the question from Lina just now. We still got a little bit of time. If you guys still have any question for Professor Amanda's, you can still let your question coming in. Maybe I could fill the gaps by asking one more questions. I think now we are living in an era of pandemics. So a lot of researchers are actually forced to work from homes. So many experimentalists actually suffer from, it's a kind of good break for them, but it's just not so desirable because they really need to go back to the labs to really carry on the experiments. So this is where the machine learnings and also computational material science can take place. So like you mentioned just now, the best way to work on this is to start collaborate. But I think before to start collaborate, experiment scientists usually they are very familiar with the work that they have. And it's good that they have something first in hand before they can approach someone like you So from your experience, Amanda, what is the best, not say the wish list is something is good that if someone knock your door with something in their hands.
Okay.
So
what would I like a
those
collaborator to come with? That's a good question. And certainly over the pandemic, a lot of my collaborators have approached me to work on something that they can do from home. In a lot of cases, they've already got a lot of the data and that they could use to make some really interesting machine learning studies. Go back to the lab book. Start recording in a numerical form all of the experiments that you've got into a nice big spreadsheet. Some of them will just give me a spreadsheet, and I can work with that. I can turn that into a data frame. I can do the programming and do all the data cleaning from that. The important thing, I think, that usually I have to explain to them when they do this is don't just send me your best results, the ones that you've put in the papers. I want to see all the things that didn't work. All of the data that you thought weren't really quite good enough to publish. That's important to keep that in if you're doing any kind of machine learning, which sounds counterintuitive. But if you want to predict that something is better, I need to know better than what. So all of those things that didn't work are important in building up an entire frame of reference and eliminating selection bias. And it comes down to all of these types of biases. If it turns out that some of that data wasn't important, the machine learning will tell us that it's not important. That's fine. Another thing is to, in a lot of cases, we do experiments in lab. We might repeat things over and over again. And so most of my collaborators tend to think that if they've done the same experiment 4 times, then they only need to give me one result. Sometimes they average it, or sometimes they just give me the best one. I'd rather have all 4. Because even though that sounds like it's giving redundant information, in terms of the machine learning, this actually gives us what's called a regularization effect. Regularization in the machine learning model helps reduce the amount of overfitting, and that actually is very useful. So some of the work that you might think is not your best work and not particularly useful, from the machine learning point of view, we love having all of that extra work. So if you're going to approach a machine learning collaborator, make sure you come to them with everything you have.
Thank you very much. I think it's about the times. So everyone's get some more insight about the machine learning work, so you know how to knock Professor Amanda doors if you wanted to have a further collaboration with her and her fantastic teams. So once again, please join me to thank Professor Amanda for your kind sharings and also insightful presentations this afternoon. Thank you.
Thank you. My pleasure.
All right, ladies and gentlemen, we're moving on to the next presentations on our keynote session number 2 by Professors Gabriele Santi from University of Messina, Italy. A little bit backgrounds. I checked the latest Google Scholar from the websites. The Professor Santi's the data that we printed in the program books needs an enormous updates, and his H-index currently is 88, with the citations is more than 30,000 at this moment. With those I-10 index paper is more than 374. Before we invite Professor Santi to share, let me briefly introduce Professor Santi. He's currently a full professor of industrial chemistry at the University of Messina, Italy. And he's also a president of the European Research Institutes of Catalysis, ERIC centers. Research concerns in the areas of applied heterogeneous catalysis, sustainable energy, and also chemical processes, biomass conversions, and environmental protections. He's also a coordinator of the European Networks of Excellence, IDCAT, and also is currently a president of IACS, which is the International Association of Catalysis Societies. In the past, also a president of European Federations of Catalysis Societies. So it's our great honors to have Professor Santi, which is really a established prominent scientist in the field of catalysis that this conference is trying to gathers all the experts to get to learn and exchange the ideas in the field in nanotechnology and also particular catalysis. So without further ado, let's welcome Professor Gabriele Santi for his talks on the electrocatalysis, role and prospects to defossilize chemicals and energy productions. Welcome, Professor Santi.
Many thanks for the very kind introduction, and let me say if it's working the presentation. I hope yes. And yes, also I apologize that is to be not in person, but it's still difficult to travel in this period. But I hope that maybe when will be the next time of this conference, we can also have the opportunity to meet all together. Well, thanks again for the invitation, and I will just present very shortly some concept about electrocatalysis, but I especially try to put these topics in the general, let me say, perspective of the direction in which we need to go, especially to defossilize chemical and energy production. I will very briefly introduce these topics and especially some content about the change that we have to face, which is to transform from a linear to a cyclic society, to move essentially to net zero emission by 2025, which is not very far. And of course, also try very short to mention some aspect that we are facing really a system change, and so we need also to think in this term how, because we have a full change in terms of technology, in terms of science, which is necessary to go in this direction, but also in terms of industry, target, societal target, and so on. There are other aspects, of course, which are important. I just mentioned here the problem of closing the carbon cycle in energy industry, but I will not have time to address this aspect. And finally, we'll move to discuss the electrocatalysis, also some aspects related to opportunity and challenges that we have. How we need to have a paradigm shift, because we need to approach from a different perspective the problem. And I will present this with a case study, which is the synthesis, direct synthesis of ammonia. Also, of course, also here there are many other aspects which can be interesting, but I hope to give some time also for some questions. So essentially,
sorry, Professor Sentis, sorry to
Yes.
interrupt. Are you sharing any slide with us?
yes, I was sharing, but probably it's not working. Let me try it again to
Yes, please.
To work. I don't know if now is working.
It's still not here. Okay, it's coming. Yep.
Okay, so apologize. Well, essentially, the slide that I showed before was just the overview of what I say, but I think that I have already explained. So essentially, this is the first slide in which this is just to summarize that we are now in a linear model in which, of course, we are using fossil fuels to many industrial or domestic use, and then we are producing carbon dioxide. I still maintain the concept of linear model, even if we take any kind of capture of carbon dioxide, because it's still the same model. Of course, what we need is to start to go to a kind of full circular economy in which essentially we need to have zero emission. This is the target that, for example, already in Europe is established, and now also in other countries is start to be established to arrive in 2050 to net zero emission. This means that to go to this, we need before to pass to a kind of intermediate situation in which we have a reduction, but we start to have a recirculation of the carbon and to intensify the technology that are using renewable energy and biomass to go in this direction. But essentially, the full model is based essentially on the use of technology like electrocatalysis, which are using directly electrical energy, small molecules like hydrogen, like water, nitrogen, carbon dioxide, and of course, we have a full recirculation of the carbon inside the process. The point is that to go from where we are now to this new model is really a full and radical system change. We have change in any area, which include technology, but also infrastructure, society, industrial interest, use of raw material, and other. So it's necessary to have clear the point that we are really in what is called deep transition, because it involves all the aspects of all society. And this means that also in terms of science, we need to evolve in this direction, because we need also to rethink several of the fundamental aspects that we have to really address these new challenges. And I will give you an example to go in this direction. And very short comment that also is important, collaboration also before was mentioned. We need also to have a very strong collaboration. In Europe, we are starting some large initiative. One of these is called Sun Energy. And if you are interested, you see here also the website. And exactly, the idea of this is to put all the stakeholders going from research to industry to society to enable the technology and the knowledge which are needed to go in this direction to develop what are called and solar fuel, and to make all the concepts which are needed to go in this direction. And of course, electrocatalysis is one of the key component in going this direction. Another problem that is important to very short to mention is that up to now, if we are including both the catalysis that we are using currently for mostly of the fossil fuel transformation in a refinery and in petrochemistry, but also if we are looking mostly of the catalysts which are needed to transform bio-based molecules, they are essentially called more or less they share several aspects similar that I call thermal catalysis, because essentially the driving force to realize the process is the heat which is provided by thermal way. However, if we need to go to this direction where we have electro, photo, and also plasma catalysis, the concepts are completely different. The catalyst, in fact, I call these to differentiate the reactive catalyst because they are based on different concepts. And so they are conceptually new catalysts, and several of the way in which we are approaching traditional thermal catalysis are not longer valid for this new area. What are the differences? Essentially, the difference that in one case, let me say, in traditional conventional thermal catalysis, essentially you have the temperature, which is providing the energy, which is to overcome the barrier of the limiting stage. However, essentially, you need to optimize these sites to improve. But when you have, on the contrary, what I call a reactive species, like you have in all the reactive catalysis, for example, in electron, you have electrons which are generated from a potential. In photo, of course, you have charge which are generated by light absorption. In plasma, these are generated by the plasma itself. When you have this species is completely changing. In the rate limiting step is typically adsorption or transformation of the reactant in thermal catalysis. In this case, is on the contrary completely different. The problem is how you stabilize, you avoid side reaction of these very, very, very reactive species, and how you can control the stage after the barrier, the rate limiting step. So it's completely different, and you need to use different concepts also from theoretical point of view to address this stage. I will speak mostly of electrocatalysis here for the simple reason that today between the different kind of approach that we have, this is probably the closer to industrialization. Of course, also plasma catalysis that are very, very interesting direction. Photocatalysis still potentially interesting, but approaches are still at too early stage, and microwave is interesting in some specific case. Just to show you that we have many challenges, is not only the traditional one, but if we are, for example, try to address some of the classical study in electrocatalysis, for example, carbon dioxide reduction, up to now the study are concentrated to form a range of possible products. However, the challenge that we have, not only in this, but in the other transformation of small molecules that are simplified here, is how to integrate this process together with the process of transformation, again by electrocatalysis of biomass product, in order to make really a complete full change in terms of product and to produce some of the products that are listed here on the right, to substitute with this process the actual process which are made by using starting from fossil fuel and use of fossil fuel both as carbon material and as also energy source. So we have really a full change challenges that we need to address and we need to develop in order to go in this direction. To go in this direction, what is important to understand is that when we are speaking about electrocatalysis, we need to go to more complex reactions that what are studied up to now. This is the real challenge that we have. We need to understand how is possible, how we can control, how we can go to in this direction. And still, all the methods that we have are still not able to address very, very well, including by computational approach. They are not really able to describe when we have complex phenomena and complex dynamics of the species of the charges interface. So there is still a new area that we need to develop and strong fundamental basis that we need to develop to try to properly address electrocatalysis for the challenge. So let me also to show you very briefly the concept that we need to change the paradigm in development of the catalyst. Because we are addressing a new kind of area. And to start in this, I think that is just good to start with the concept that electrocatalysis is not electrochemistry, just in presence of a catalyst, but we need really to understand how we can integrate the concept to go to a new kind of approach for the system. And just to show you that it's also different from the normal thermocatalysis, this is an example in which you induce a surface reconstruction by application of a potential or a charge on a particle, and this is quite obvious. However, still, of course, this is reversible and change completely the behavior of the system. So it's not that you are just have reactive species like electron, but you are also changing the nature of the catalyst because you are applying charge to the catalyst itself. And another aspect is that was mentioned before also that, of course, when you have a particle with different shape, you have different kind of active sites which are exposed at different corner and age and so on. However, this is there is a lot of study on this which demonstrate this. When you have electrocatalysis, there are other aspects which are important, and here is illustrate one, because when you are applied a potential, a charge to a particle, you are creating also a localized electrical field at the surface of the particle. And how you see here in this picture, this strongly depends on the nanoparticle shape. This means that you create a completely different kind of electrochemistry based on the form, not because you have different active site, but because you are creating an electrical field which is associated to the shape of the particles. And for example, this is one example of taken from carbon dioxide electrocatalytic reduction, in which you show that if you have cubes or nanospheres below some dimension, you have a better performance current density, in this case related to a copper foil. But this is not related because you have different active sites. This is the usual interpretation, but due to the fact that you have a different electrical field associated to this particle size. There are many other challenges. We have not the time to enter in all. I just say that we can develop a new kind of catalysts which are specific for electrocatalysis and also new catalyst concept. We can realize also from industrial point of view process intensification. We are opening new change. I will just very brief later say something, but let me enter shortly in the case example of synthesis of ammonia. This is just to show you that the actual process is a multi-step, high pressure, temperature steps, which has a large impact on carbon dioxide emissions. So something like between 10, 15 tons of carbon dioxide are produced per tons of ammonia. And on the contrary, if you go to a direct synthesis by electrocatalysis, you operate in much milder condition, and you can have a reduction of the carbon footprint, something like more than 90%. So you have a very drastic carbon footprint. This is an approach which is suitable for distributed production to produce ammonia to transport from remote regions. So there are many interest aspects. But let me just example you limited to a relatively homogeneous set of electrode, in this case based on nanocarbon. These are some examples taken from literature about some of the model that was proposed. Here we see, for example, a dimer of iron molybdenum, or single site of nickel, or doped phosphorus, or doped boron. So there are many others. The point is that if we are looking to all the literature results, here are just a small set of homogeneous that you see on the left side. You see that for a relatively all these results are in a relatively narrow space here in terms of Faraday efficiency respect to current density, respect to, let me say, the range of industrial interest. So if you are looking from this perspective, all the results looks very similar. However, if you are looking then to what is proposed for this catalyst, you see here on the right a list, for example, of the catalyst in which there are completely different kind of mechanism, normally supported by DFT method, going from defect site to doped sites to iron sites, different kind. So the question is that how is possible for a relatively limited range of change in the performance to have a so large range in terms of the mechanism, each of these which is proven by theoretical and other methods. The problem is that we can first say that probably the current approach are not the right one, because they are just making some incremental increase rather than really the change which is needed to go in this direction. And also that probably the current approach, including by theoretical method, but not only limited to this, they are not really able to describe in the correct way the complex phenomena which are present. So because they are essentially using methods which are derived from thermal catalysis and which are not suited for this different kind of catalyst. So we have different type of catalyst. We need to develop also different concepts. We cannot just use the same concept to describe a different context and different rule. And of course, we can discuss long, for example, what are the limits also in the current approach in terms of mechanism. Normally, for example, there are many adsorbates which are important and which can even induce reconstruction, which is not taken account. There is a complex dynamics of the gas-solid interaction, which is not a proper account. There are many deviations from ideality. I just include some examples, especially there is a lot of amorphous phase which are not on the surface, which are not accounted. There are many localized charge which are important, which are also not included. And of course, this is inducing also reconstruction strain and other deviation from the crystalline arrangement. Of course, there are progress. It's possible to go in this direction to try to include this more complex situation. However, when we are going to reactive catalysis, and especially for electrocatalysis, we have additional problem in which we have a dynamic of reconstruction, we have change interface, heterojunction, which stabilize the species. We don't have a uniform, as usually consider a uniform potential, but this is strongly depends on the nanostructure. We have a symmetric charge distribution and other aspects. So essentially, why the classical method are failing? Because even if the classical method of mechanism, they are considering a localized approach on the active site, in practice, what this effect is mediated from the temperature effect and associated effect from phonon to other, which essentially mediate this effect. On the contrary, in electrocatalysis, for example, due to the fact that we are working at lower temperature and in presence of the potential, we have an amplification of this local effect. And this is the reason why, if we are applying the usual system, they fail to describe it in a correct way. I would like to give a few minutes also for questions, so I will stop here. But if you are interested on these topics, I suggest you, for example, a series of recent review that we publish on these topics, where you can find also some better indication about the aspect that, of course, I was quite brief. And I suggest also a series of 3 articles on catalyst review that we published exactly on these topics, where there is more detail and data about all these aspects. So, conclusion, the ongoing transition in energy and chemistry is leading to a system change. And to address this system change, we cannot just implement the current way of thinking. We need to develop a new alternative way, and we need to follow this change, because we have a change not in some aspect, but in the full system. And electrocatalysis, we are convinced that it will play a role important for the future, for addressing this transition, but we need to pass to make electrocatalysis of complex transformation, so address the complexity in this. And of course, acceleration in this direction can require to have a strong community which operate in synergy. And I just give you one example, but this can be more general for all the different communities. Okay, thank you for attention.
Thank you very much, Professor Santi, for your kind sharings this afternoon. Let's begin with the Q&A sessions. The first ones are from Dr. Alia. Okay, dear Professor Santi, thank you for your great sharing. May I have your opinions on the prospect of organic quantum dots, such as carbon quantum dots, as transducers in photocatalysis applications?
Yes, good question. I think, yes, they can play really an important role, essentially because what we need is to really improve the system in which we can capture light in a large, let me say, spectrum. Because up to now, all the system are not very effective in this direction. This is not only, you need also to redesign, because essentially, even if there is a lot of indication that even if you are improving the light absorption, this is not improving the efficiency, for example, solar to fuel efficiency in the transformation, essentially because also start a number of additional problems in terms of side reaction and so on. But of course, this is one important element to go in this direction.
Okay, thank you. We move on to the second questions by Dr. Lee Hui Woon. Okay, dear Professor Santis, thank you for your sharing the good topics of e-refinery systems for the renewable energy productions. Does the electrocatalytic systems applicable for the industrial scale application based on the cost concern as compared to the thermal process?
Yes, this is a direction in which, of course, there is a directive. There are already some example of projects which are at least close to industrialization. The problem is that, as I explained, you have these challenges because from one side, if you are making simpler reaction, this is more simple. For example, if you are making two electron or electrocatalytic reduction, is more simple than if you go to more complex electrocatalytic reduction. But at the same time, the real added values that you have is when you go to these, because you reduce the steps. The advantage, yes, you have the cost of electrical energy, but at the same time, you have the great advantage that you are strongly decreasing of the number of steps. And this is the real main advantage that you have. And in fact, there are already some projects which are at least at the level of pilot, which are we hope to in the near future to arrive to commercialization.
Okay, we still have 1 more minute. Maybe we can take the last questions. Actually, it's a lot of questions, Prof. Santi. I think I'll ask the secretariat to compile the question and then forward it to you for the further. Yes. And let's end this session with 1 more questions by Dr. Lai Li. Okay, dear professors, in the electrocatalysis process of biomass conversions, how can I maximize the atoms and energy efficiencies while keeping the generated powder densities at low temperatures?
Well, essentially, the atom energy efficiency depends really on not only on the design, but also here there is an integrated effect, because up to now a lot of loss in the performance are not only related to catalyst itself, but all the device. So is a combining engineering between the electrocatalyst itself and the device, but still is possible in some reaction to achieve a very high atom energy efficiency. So I'm convinced that this will be still possible. Of course, the problem is that we need to address more seriously all the problem of selectivity, which is still not full understood also from mechanism point of view.
Okay, great. Thanks so much, Professor Santi. It's our great pleasure to have you with us today. Thank you for your fruitful sharings.
Thank you.
Now we have reached at the end of the sessions, but today's session is not end yet. We have a parallel session after this, but we just end this afternoon's plenaries and also the keynotes sessions. Thank you for your kind participations. On behalf of the MICNC's 2021 organizing committees, I would like to seek your kind cooperation to fill up the feedback form as given by the session's moderators in the pool box. So you are invited to join the rest of the events starting, I think, 10 minutes times. So hope to see you all again in the other sessions. Thank you and stay safe. Bye-bye.